This is the first video that we're gonna introduce to torque. And what you need to know from this first video is that torque is the same as the force. So the force makes an object to accelerate linearly, and torque can make an object to accelerate angularly. So when you apply a force, like you see it in this picture, the more force you apply, the faster the wrench is going to be moving, and you can cause it to accelerate. There are two different formulas for torque. One of them you see at the bottom, and the torque is equal to, so it's the same as force, but it's a rotational force. So it has a letter tau. So this letter that you see right there at the bottom is tau. So this is tau. And it equals to the force that you apply times the distance, how far do you apply this force, times sine theta, and theta is the angle between the force and the, in this case, the wrench. So you see, if the angle is 90 degrees, you will get the largest torque, and if the angle is 0 degrees, let's say if you didn't apply it this way, but you applied it that way, so if your force was this way, then you would have 0 torque because sine of 0 is 0, and the wrench would not be rotating. So this is one of the formulas. Another formula, like before, we would say that the force is equal to ma. So because torque is also force but rotational force, the torque has the formula of, instead of the mass, we have rotational inertia and acceleration, rotational acceleration. Rotational inertia has different formulas, so there's not one formula for every single case. Every single one of them is going to be different inertia. You only will have to remember, they don't give it to you on AP exam, and I haven't seen many questions related to this. You have to understand the concept of it, but not memorize the formula. But in our classroom, I want you to memorize a formula for a few inertia, and I'll show you later on in this video. So the torque is equal to, instead of the mass times acceleration, it is inertia times angular acceleration, because torque causes an object to accelerate angularly. So as you see here, the force is equal to ma, and torque is going to be equals to inertia times angular acceleration, or force times the distance, how far the force is acting from the point of rotation, times the sine of angle between the point where you apply to the object that you apply the force. And torque is going to be measured in newtons times meters, because you have newtons times meters, because you have force times the distance in the formula. So for inertia, you will have different formulas. So here I have for you the whole choices that you can choose from, different formulas. The different objects will have different inertia. And what you need to know is only these two. You need to know inertia of the disc, and you need to know the inertia of the cylinder. And let me explain to you why these two guys are different. So inertia has mass times radius squared. And in the disc, all the mass is spread at the edge of the shape of the disc. There's nothing in the middle of point of rotation. So if this is point of rotation, there's nothing in the middle. And inertia is the opposition of the change. So the more inertia object has, the lazier the object is. So inertia for the disc is larger than the inertia for the cylinder. Cylinder has mass within the cylinder inside, so it's filled up with a mass. And the objects that are, or the particles that are closer to the center of rotation, so here is the center of rotation, and the particles that are closer will rotate faster than the ones that are farther away from the point of rotation. So the inertia of the cylinder is 1/2 of the inertia of the disc. So again, the inertia is going to have different formulas. Here you see mr squared, so that one is for the disc, and for cylinder you would have 1/2 mr squared. And also angular momentum So linear momentum has a formula. So the linear momentum has a formula of mv, mass times velocity. Angular momentum also has a formula, mass, but we use inertia, times angular velocity. And if I say that, just for this case, where inertia is equal to mr squared, and if you remember the formula for the relationship between the linear velocity and angular velocity, they have this relationship. So if I replace angular velocity with v over r, then r and r cancels, and I have angular momentum is equal to I times omega or m r v. So that's the formula that you see as well in our lesson right there. And kinetic energy, I mentioned it when we did angular motion. So kinetic energy 1/2 mv squared. Here kinetic energy is 1/2. Instead of mass, we have angular momentum. Again, momentum is going to depend on what kind of shape you're using. But for the disk, it's going to be mr squared. And then, so the kinetic energy is equal to 1/2 inertia times the angular velocity squared. And just repeating, the torque is equal to the formula of the torque, repeating right here. And let me derive the last part of the torque right here. So the torque is equal to inertia and angular acceleration. And this one is for the disk, mr squared. Different formulas will be for inertia for different objects, but for the disk is mr squared. And then for acceleration, I have change of angular velocity over the time. So the torque is equal to, again, mr squared. And change of the velocity, let's say we start with initial 0, so that's going to be the final only left. And I can write as change of the linear velocity over the radius. So if I replace angular velocity with the relationship to the linear velocity over t, then I have r's canceled, and I have mr change of the velocity over t. But that is the same as angular momentum, or change of the angular momentum over the time. So this is where the last part of the formula appears, or coming from. So let's look at this first question that we have here. Two disgruntled businessmen are trying to use a revolving door as shown. The door has a diameter of 2.6 meters. The businessman on the left exerts the force of 625 newtons perpendicular to the door and 1.2 meters from the hub center, while the other one is on the right exerts the force of 850 newtons perpendicular to the doors and 0.8 meters from the hub's center. Find the net torque of the revolving door. So the net torque is equal to, and torque is going to have the direction. So if the torque is, it's the same as your unit circle. If the torque is applied this way, it is positive, and if the torque is applied this way, it is negative. So if the torque causes an object to rotate in this direction, then the torque is negative. If the torque is asking the object to rotate in this direction, then the torque is positive. So in our case, I have the man on the left is causing the negative torque, and the man on the right is causing the positive torque. So the man on the left is applying the force of 625, so it's negative 625, and the distance that he's applying force is 1.2 meter away. And the man on the right is applying 850 newtons, and the distance that he is applying at is 0.8. So the net torque is equal to negative 70. So negative 70 newtons times meters. So here's the next question. A man applies a force of 300 newtons at an angle 60 degrees to the door 2 meters from the hinges. Find the torque on the door choosing the position of the hinges as the axis of rotation. So here is your axis of rotation. And suppose the wedge is placed 1.5 meters from the hinges on the other side of the door. What minimum force must the wedge exert so that the force applied in part A won't open the door? So let's write everything that is given into the formulas. I have the torque is equal to force times the distance, and sine of theta. The force is 300. The distance is 2 meters. And the angle sine of 60. And so that will give me 520 newtons meters. 520 newtons times meters. And it's in positive direction because it causes the door rotate in a positive direction. And for the second part, suppose that there is another force B is applied and opposing the motion. So that means B, we have to find the distance, correct? So we have B times the distance. Oh, actually the distance is 1.5 meters. Times 1.5 meters. So it's the force times the distance. Must be equal to exactly the same torque that the other person is applying. So that is 520 newtons times meters. And so from here, I see that B is equal to negative, and this has to be in the negative direction, so it's negative 347 newtons, the force that needs to be applied in order to not, and the angle was 90 degrees, so I didn't have to worry about the angle, so the angle is 90 degrees. So sine of 90 is 1. Here's another concept that we should go over, and this one is called condition for equilibrium. So before we say equilibrium is when an object is not accelerating, the net force is equal to 0 because all the forces acting on the object cancel each other. So if the net force is equal to 0, there's no acceleration. And we still will stick with that rule, but we also can say that the torque must be equal to 0, then the object is not going to rotate. So in this case, for total conditions for equilibrium, you have to say the net force is equal to 0 and the net torque is equal to 0. Let's look at this question together. A uniform ladder 10 meters long and weighing 50 newtons, that means the mass is 5 kilograms, rests against a smooth vertical wall as shown. If the ladder is just on the verge of slipping, when it makes 50 degrees angle with the ground or with horizontal, find the coefficient of static friction between the ladder and the ground. So we can put the forces acting on the ladder. So the force of gravity is always from the center of gravity or center of mass. And we're going to learn this concept a little bit later, but for now you just have to know that it's a uniform ladder, so the mass is distributed evenly. So we have the first force right here, 50 newtons, which is mg. So this is mg. Then the ladder is not slipping off because there is force of friction. So I'm going to call it the lowercase f. And also there is a normal force coming from the ground acting on the ladder. And there is some force, cannot call it normal again, but I'm going to just call it some force from the wall on the ladder. So these are the forces acting on the ladder, and it is an equilibrium. That means the sum of all the forces and sum of all the torques equals to 0. So at first I'm going to say sum of all the forces equal to 0. And I have horizontal forces. So that is the friction, I'm going to choose positive direction, minus F equals to 0. In other words, the friction force is actually equal to that force from the wall. And then the next one is the normal force minus mg for vertical forces equals to 0 because, again, there's no acceleration. And that means the normal force is equal to mg. So we could rewrite it this way. And I'm going to do for sum of the torques equals to 0. So the torque formula is force times the distance sine angle, right? And it always starts distance from point of rotation. So I'm going to choose this blue dot as my point of rotation. And if I say friction times the distance, which is 0, that will cancel. And I will say normal times the distance, but that's the 0 distance from the point of rotation. That will also cancel. And also, I have to remember that any torque that is causing an object to rotate in this way is negative, and any torque that is causing an object to rotate in this way is positive. So let's write the torques acting on the object. So friction times the distance, which is 0, we can cancel. Normal times the distance, which is 0, we can cancel. There is the force mg acting on the ladder, so I'm going to write mg. And mg is causing it to rotate in the negative direction. It's a clockwise. So I'm going to write mg. And the distance it's locating at is the distance, the length over 2. So it's L over 2. And another force is acting is F. So the force F would make the ladder rotate in the counterclockwise, which is positive direction. And that is F times the letter. Oh, I forgot the sign. So here we need the sign. And the sign of an angle, this angle is 40 degrees. And then plus the force, which is causing it in the counterclockwise direction. Distance is L, the length of the ladder, from the point of rotation, which is the blue point. Oh, let's make it the red point right here. And times sine. And this angle theta and that angle theta is the same, so that is 50 degrees, and that is equal to 0. Also, the force of friction is equal to F, and I can also write it as mu times N. And your N is equal to mg. So I can replace the force with mu times mg. And so I'm going to have negative, but let's times them all by 2 so I don't have to write fractions anymore. So I'm going to times the first term by 2, then the fraction disappears, negative mg. And then I have L, and then sine 40 degrees, and plus, times it by 2, so 2 will appear over here. And then instead of F, I have mu, and times N, which is mg, and sine times L, and then times sine 50 degrees equals to 0. And I have 1, 2, 3 terms that I can divide by mg. So I'm going to cancel mg from each one of them. Cancel mg and cancel mg. And then your mu is equal to, the coefficient of friction is equal to, oh, I could cancel L as well. So I can cancel L and I can cancel L. And it will be equal to sine of 40 divided by 2 sine of 50, and that is equal to 0.42. So the coefficient of static friction between the ladder and the ground is 0.42. I wouldn't be able to solve this problem alone with only forces given. So if I only used forces, there wouldn't be enough information to solve this problem. So it's nice to sometimes use sum of the torques equals to 0 for equilibrium, because then it's easier to solve for the variable that we do not know and looking for. Here's the next question we're going to look at. A schoolyard teeter-totter with a total length of 6 meters and a mass of 36 kilograms is pivoted at its center. A 18-kilogram girl sits on one end of the teeter-totter. Where should the 210 Newton boy sit in order to hold the teeter-totter leveled? So if I have the teeter-totter and it's supported by in the middle, so that means there is the normal force acting on the teeter-totter, and there is the force of gravity acting on the teeter-totter. And then 18-kilogram girl sits on one end of the ladder, so she sits all the way at the end, and she is applying the force of 180 newtons because her mass is 180 kilogram. And the distance I do not know, so it's halfway through, so that is 3 meters because the teeter-totter is 6 meter long. My point of rotation is gonna be where the teeter-totter is supported, and where should sit the other boy with the weight of 210 newtons. So he is going to be sitting at some distance, let's call it x. And where should he sit so that the teeter-totter is going to be staying in the level position? So I can say that sum of the torques again in this problem is going to be equal to 0. And the torques are acting, I have to always think again, this direction is positive, that direction is negative. So counterclock direction is negative, and counterclock direction is positive, and clockwise direction is negative. So looks like 180 is going to be positive. So I have 180, and the distance from the point of rotation is 3 meters. And the angle is 90 degrees, and then negative 210, because sine of 90 degrees is 1, and then negative 210 times the distance I'm looking for, and that is equal to 0 because some of all the torques acting on the object will be equal to 0 because the object is not rotating. And then I can divide every single term by 3, so I'm going to divide by 3, by 3, by 3, so I have 180 equals 270x. I move it to the other side. I can also divide all of them by 10, so x is equal to 18 over 7, which is equal to 257 meters. So the boy should be sitting 2.57 meters away from the point of rotation, from the center of the teeter-totter, in order for them to stay leveled. Let's look at this question too. If the angular velocity of the 0.5 meter in the radius pulley in the figure is negative 9 radians per second at a given time, and its angular acceleration is negative 3 radians per second squared, what is the angular velocity of the pulley 1.5 seconds later? And what is the angular linear distances did the mass travel over this time, and how many revolutions did the pulley make? So this is like angular velocity type of problem, so I can find the final velocity by saying it is initial velocity plus the acceleration times the time. So if I plug in my numbers, I get negative 13.5 radians per second. So I have this part, and then they ask me linear and angular distance. So angular distance is equal to average velocity times the time. So that means negative 9 plus negative 13.5 divided by 2 and times the time, which is 1.5. So angular distance traveled is negative 16.875 radians. And to find linear distance, if you remember the formula, the linear distance is equal to r times theta. So I can find the linear distance by r is given 0.5 and times theta is 16.875, and the negative sign just tells you in which direction it moved, so I don't really need to plug it in as negative. So the linear distance is 8.4375 meters. And then they ask you to find how many revolutions. So one revolution is 2 pi radians. So if I divide this number of radians by 2 pi radians, which is 1 revolution, I will know how many revolutions the happened over this 1.5 seconds, which is 2.686 revolutions. So 2.686 thousandths of revolution. Here's another question that I want to solve in this video, so I'm gonna pause it and let you read it, and then by the time you unpause it, you will have everything given, everything that is given written for you. So go ahead and pause it. So I have the force that is acting 2.5 newtons, the radius at which it is acting 0.25 meters, the time for as long as it acting 0.15 seconds, and the mass of the Lazy Susan is 4 kilograms. I'm gonna use this trick. This is the linear expression, so force is equal to ma, and I simplify it until I find change of the momentum over the time. So I'm gonna use this trick for torque. So torque is the same as force, and instead of the mass, I have inertia times angular velocity and angular acceleration, and then I have inertia times change of the angular velocity over the time, so that is change of the angular momentum over the time. And also another formula that I know is the force times the distance and sine theta. So I can set them equal to each other, and I can say force times the distance sine theta is equal to change of the momentum over the time. And so I use these two formulas that equals to each other. And then from here, I can see that change of the momentum that they ask you to find in the first question is equal to 0.09375, and that is kilogram meters squared over seconds. So that is the A part. And then for B I will have but first I have to find the inertia, which is the disk, which is 1/2 mr squared. So if I plug in my numbers, I get, it's the formula that I told you that I want you to remember. So that is 0.125 kilogram meters squared, because it's kilograms times meters squared. And then I'm gonna use this for this part right here, that I'm just gonna rewrite it. This is equal to inertia, the mass, times change of the velocity. So from here I can find the change of the velocity is equal to change of the momentum that I just found, divided by inertia that I also just found. So that will give me 0.09375 divided by 0.125. That gives me 0.75 radians per second. So I find out by how much the velocity changes, and they ask you if it started from rest. So if initial velocity was from rest and velocity changed by this much, then the final velocity of Lazy Susan is going to be 0.75 radians per second. And this is the last question I'm solving in today's video, so we will stop here. So this was introduction to the torque, inertia, different types of inertia, and angular momentum. And there's going to be more questions solved in the future where I'm using the same concept. The description for the future to follow videos are in the description of this video, and I will see you in the next video. Thank you for watching this one.